Welcome to the Harper Classroom. I'm Dr. Harper. This lecture video is Introduction to Operations Management using Break-Even Analysis with Excel. A description of operations management can be a transformation of inputs to outputs. I will develop this in three stages: the input-output model, which establishes a structure; operations strategy, which introduces terminology and problem-solving approach, which is the quantitative aspects of operations management. Let's start with the input-output model. In the input-output model, the input are resources, which are facilities; material, which is inventory; equipment and labor, which is people. The output is product and/or services. The transformation process could be design operations, manage operations, or control operations. In design operations, it could not only be a design of operations, but recognizing the capability of the design. Managing operations is conducting operations efficiently and effectively. Controlling operations is change. You can control operations by improving them, by changing them, by tearing down the old and incorporating the new, especially with new technology and globalization. So this is an overview, but there are also modifications. Three types of functions: strategic, tactical, and detailed. A strategic function is a long-term decision that can significantly impact a company. Tactical is medium-term, more planning. Planning on how much inventory you need, planning on what your production is going to be, planning on how many people you hire. Detailed is day-to-day operations to make things run smoothly and efficiently. Another modification is the type of industry. There are many types of industries. Here are three types: continuous, intermittent, and service. Let's start with continuous and intermittent. There are many types of industries, from continuous to intermittent. Here are a few examples. Let's look at continuous. One type of continuous industry is a repetitive industry. An example would be an assembly line, mass production. Every station has discrete elements of work that is repetitive continuously. Another type of continuous industry is a process industry. Here's an example of an oil pump station that's a mechanical process. You can also have a chemical process, like steel manufacturing, or a biological process, like forestry. One type of intermittent industry is batch production. An example of batch production is a textile shop, where each textile run is one product line of garments, and then you shift over to another product line. Within a production run, it could be continuous repetitive techniques, but the changeover to the other product line would be intermittent techniques. Another example is a bakery, where the production runs are much smaller, but you still have changeover to different products. Now, when the number in a batch run becomes very small, and you don't have changeover, then you move to something called a job shop production. So here's an example of a machine shop and a research group for PET brain imaging machines. So this machine shop can fix one machine, or replace parts on one machine, or perform preventive maintenance on a small number of machines. The next type of industry is the service industry. The service industry is defined when the customer is part of the operations, and the level of customer involvement defines the type of service industry. Next, we have objectives. We start with monetary objectives to maximize profit and minimize cost. Then we move to time. The faster we can do it, it becomes a competitive advantage. Then quality. We define quality, and then we optimize it. So this represents an overview of operations management. Now let's go a little bit deeper into operations strategy. I will define strategy as a sequence of decisions leading to an objective. And when those decisions are operations decisions, then that becomes a strategy. We'll make decisions in three areas: product design, process design, finished goods inventory design. First, product design. We'll look at two types: customized product design and standardized product design. For customized, this is designing a product specifically for one or a small number of customers. An example would be a computer lab designed specifically for an operation. Another would be the architecture of an airport. The other would be a logo. And logos are required by law to be customized. Standardized is the same design for everyone. An example would be the Environmental Protection Agency that requires certain standards to be met. The Food and Drug Administration also has standards for food and medications. And the Corps of Engineers will have standards that have to be met in their construction that will not be compromised. But often a product will have a combination of these two. For example, the lab might be customized as far as its use is concerned, but each element or each monitor could be standardized. Next is a process design. Let's start with two types of manufacturing process designs, product-focused and process-focused. First, product-focused. An example of a product-focused process design is a conveyor belt or an assembly line, where the operations are focused on the needs of the product as they pass the workstation. The advantage of the product-focused process design is high volume and low cost. The disadvantage is capital investment, redundancy of the operations for different product lines or different conveyor belts, and low product variety. The next is process-focused. An example of a process-focused process design would be a job shop. The advantage of a job shop is flexibility, because as a product comes in, it can go to the table saws or drill presses, and that could satisfy any type of product. So therefore, it supports customization and product variety. A disadvantage is higher cost per unit because of the scheduling and movement, greater cycle time, and also increased queue length. But these can also be combined. One common combination is cellular manufacturing. In cellular manufacturing, you create cells, and within each cell, the operations are laid out according to a product-focused design. So the product-focused characteristics within a cell will be high volume and low cost. But between the cells, you'll have a process-focused layout, because each cell may produce a product or a subassembly. So the way they are combined, you can create product variety, customization, and flexibility, which are process-focused characteristics. Next, we have service process design, and the amount of customer involvement in the operations define the type of service design. We have quasi-manufacturing, customer as participant, and customer as product. As examples, quasi-manufacturing could be a string quartet, because the customer is listening, but they're not really involved in creating the service. Next, we have customer as participant, where we have the customers are participating with the consultant. The consultant has to determine what the customers want and need, and the customer has to determine what the consultant is capable of doing and can deliver. Next is customer as product. The example is the medical field, because the customer is the result of the service. The different service process designs require different skills from the server. It also indicates different definitions of quality for the customer. But the way all these is put together will define your operation strategy for service process design. Next is the finished goods inventory. There are two types, make to stock and make to order. An example of a make to stock would be the bread aisle in a supermarket. The bakery produces that bread to create inventory, and demand is met out of inventory. An example of make to order is Dell computers. You call and give them your order, and then they produce your product based on your order. Well, these also can be combined, and the way they're combined is the push-pull boundary, where the make-to-stock operations is really a push process, where you produce to make inventory and you push it downstream to the customer based on forecasted demand. The make-to-order is a pull process, where you produce to satisfy your order fulfillment based on realized demand, and that realized demand is the order. So where the pull process or order fulfillment meets the inventory or the push process, that's called the push-pull boundary or the decoupling point, where you decouple the inventory from your orders. And this is used in design of inventory systems. So these are three important decision areas that make up an operation strategy. Next, let's look at the problem-solving approach. In the problem-solving approach, I'll develop this in three stages: recognition of problems, application of techniques, and communication of results. And I'll use a break-even analysis. In the break-even analysis, let's assume that we have a company that's going to select either an automated process, cellular process, or job shop process within its factory. They've estimated the fixed cost per year and variable cost, so cost becomes one criteria in their decision process. First, let's recognize that this is a break-even problem. The first is the extreme value approach. What if the annual production was very low, 0 units, the variable cost would be 0, and the fixed cost would be the cost. Well, the minimum cost now is going to be $75,000, which is job shop. So for low production, the minimum total cost is job shop. That's a principle. Next, for very high production, like 1 million units, well, the variable cost is $2 a unit for automated, so that's $2 million plus $110,000 for the fixed cost. For cellular and job shop, it's $4 million and $5 million. So now the minimum cost now is the automated. For very high production, automated will be the lowest cost. So when you look at the lowest cost, for low production, it's job shop. For high production, it's automated. Well, since those are different, then there's a production somewhere between 0 and 1 million such that these two costs are equal, and that's break even. So a break even does exist. The second type is problem structure. When the fixed cost decreases while the variable cost increases, that structure indicates a break-even analysis. For example, suppose the 2 and the 5 were exchanged. Then right here, the fixed cost is always the job shop as a minimum. The variable cost, the job shop is always a minimum variable cost. So the job shop is always a minimum, and there is no break-even analysis. So now that we know that a break-even analysis exists, the second is application of techniques. In the application of techniques, there are 2 steps. The first step is understand the problem. When we look at this problem here, the cellular and job shop, if we produce 0, the difference is $5,000. Cellular is $5,000 more dollars than job shop. But when we start producing, we save $1 a unit of production. So if we produce 5,000 units, then 5 times 5 is 25 plus 75 is 100,000. 5 times 4 is 20 plus 80 is 100,000. The cost is the same, and that's my break-even. So 5,000 is the break-even between cellular and job shop, because 5,000 units of production, the costs are the same. So for very low production, the job shop will have the lowest cost. How low is low? Everything below 5,000. The automated and cellular, the difference is 30,000, the savings is $2. The production of 15,000 units, which is half of 30,000, would have the same cost for automated as cellular, so 15,000 is the break-even between automated and cellular. First, understand the problem and get a feel for what the answer is. Then, we validate that solution in our understanding with the technique and the mathematics. So down here between the break-even automated and cellular, we bring the fixed cost down, we bring the variable cost times X, our production, annual production, solve for X, we get our 15,000. Between C and J, cellular and job shop, we bring our fixed cost down, we bring our variable cost down times X, solve for X, we get our 5,000. So this is in line with our understanding. Both of these have to go together, because if our solution from our mathematics do not match our understanding, then something's wrong. Either our understanding is wrong or our mathematics is wrong. Both of these have to go together. So now let's solve this with Excel. So let me bring in Excel, and notice I've already typed in the fixed cost and variable cost, and the equations here, solving for X up here, would be these equations here. So let's bring this in and actually solve this with Excel using these equations. So this is going to equal, open parenthesis, fixed cost minus fixed cost divided by the variable cost minus the variable cost. And there's our 15,000. This is going to be our fixed cost minus our fixed cost divided by the difference of our variable costs. And there's our break-even, 5,000 and 15,000. Let's find the cost to demonstrate the minimum cost. Let's start with 15,000 and 5,000. So the cost here for the automated is going to equal our fixed cost plus our variable cost times our 15,000. We want our demand 15,000 to be fixed, so we come up here to G1, highlight it, F4 to freeze it, return, and then we can copy that down. And we can see for 15,000 the minimum is going to be 14,000. It's the same for automated and cellular. Same for 5,000. That's going to equal our fixed cost plus our variable cost times our demand, our production, and we want that production to be constant. So again, we highlight H1, F4 to freeze it, return, and then we copy that down. Delete, delete, and we see the minimum cost is $10,000. It's the same for Cellular and Job Shop. So we can demonstrate the break-evens. So now let's see how to plot this in Excel. We want our graphs to be a straight line, which is going to be y equals a plus b times x. We start with automated, copy, and paste. And then cellular, copy, paste, paste, and then Job Shop, copy, paste, paste. So this will be the A, and this will be the B. Now for X, we'll start with 0, and then this is 5,000 and 15,000, so let's let X go to 20,000. And then we copy, and paste, and paste. And then for Y, that's just going to equal our A plus B times our X, and we just copy that down. And so there we've set it up. Now we'll go to Graph. Up here, Insert. We'll take a chart here. We'll take this chart. We'll have a line chart with dots. And let's do this one. Okay, then we select our data. We're going to add for our automated. Our X values are going to be these. And then our Y values are going to be these. Okay. And then we want to add another one. And this next one's going to be our cellular. Our X values now are going to be 0 and 2,000, or 20,000. And then our Y values are going to be given by these. And then finally we want to add a third one, which is our Job Shop. Our X values are here. Then our Y values are going to be given here. And there's our plots. Now we'd like to have a title up here, so we add chart elements. Here the chart title. And so we wanted the top, and that's going to be the break even analysis. So I'll put that up there for now. And then down here we want a legend. Add chart, here's a legend. And let's make it to the right. And there it is. Let's bring it in here and expand this. And so now we can put a box around this. On our format, box it in. We can box that in. And we'd like to have some axis titles here. Come up to Add Chart Element Axis Titles on the horizontal. And this is production. And let's click this and raise this so we can actually see the title. And there it is. Over here, this is axis title on the vertical. This is going to be cost. And again, we can click this and move this in so we can see that title and the title up here. Right click the font. We can change the font if we want to Arial. We can bold it. We can come down here and underline right here. And so we can just start format the graph the way we want. For the communication of results, I'm using a graph as a presentation. But in business and operations, communication is essential in the application of quantitative methods. So for the problem-solving approach, we have recognition of problems, application of techniques, communication of results. All three of these or an important aspect of applying quantitative methods. So this ends the lecture video on Introduction to Operations Management using Break-Even Analysis with Excel. I hope this helps. Thanks for watching.